Now, let's just make some observations about sequences. What we want to do is we want to be able to look at some sequences and determine, does the limit exist? In other words, do these sequences converge or not? Well, let's consider an alternating sequence. Let me just make an alternating sequence here. Okay, a real simple one. It goes from positive, negative, positive, negative, positive. Just goes back and forth. Now this right here, let's call this A sub n. Now let's think about what would happen if we looked at the absolute value of A sub n, the absolute value of A sub n. Well, what would happen is everything would just be flipped over to the top. So it would look something like that, okay? Now, one of the observations we can make at this point is that A sub n is less than or equal to the absolute value. Every term of this A sub n is going to be less than or equal to the absolute value of that term. That's pretty easy to see that would be the case. Now, let's look down here and let's suppose that instead of the absolute value, let's do the negative absolute value. So here we go, we've got the negative absolute value. Well, what that's going to do is it's going to take all the positive terms and flip them down to the bottom. So, you're going to have something that looks like this, something like that, because it's just taking the negative of all the absolute values. In other words, everything's going to be negative. Now, if you give that some thought, you can see that this A sub n is going to be greater than or equal to the opposite of the absolute value of each term. Each term of A sub n is going to be greater than or equal to the negative of that term, or the negative absolute value of that term. So, in other words, what I'm saying is that this A sub n is between this one and this one. Now, let's suppose that the limit of the absolute value of A sub n is equal to 0. Well, if that's the case, automatically we know that the limit of the negative absolute value of A sub n is equal to 0. Now, if this is the case, think about that squeeze theorem. You've got this limit is 0, and this limit is 0, and this is in between. Therefore, the limit as n goes to infinity of A sub n is also equal to 0. In other words, if the limit of the absolute value of the sequence converges to 0, if that limit is 0, then the limit of the alternating sequence is also 0. Okay, so now a couple other things I want to take note of, just mainly some terminology. If you look at, let's just look at a couple of, let's look at a sequence here, a couple of sequences. Okay, a couple of sequences. Um, okay, so let's suppose that we've got this sequence right here. Okay, now notice that sequence is getting bigger and bigger. The a sub the values of the sequence, the terms of the sequence are getting larger and larger and larger. In other words, in this case, what you have is that A sub 1 is less than A sub 2, it's less than A sub 3, and so forth. That just goes on and on. In other words, every term is getting bigger and bigger and bigger. Now, this is monotonic. Okay. Now, let me do another one here. Okay. And we're just defining some things. This one, let's suppose that every term of the sequence is the same. Okay. Notice every term of the sequence is equal to the others. This is also monotonic. Now you can have a variety. Okay, you can have a situation like this. You could have increasing, 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 stays the same, stays the same, stays the same. But notice that A1 is less than or equal to A2, less than or equal to A3, and so forth. Okay, this right here, this, when you have a sequence behaving this way, we say that's monotonic. And in particular, this is monotonic non-decreasing. Okay? So we have a monotonic non-decreasing. It's either getting bigger and bigger and bigger or staying the same. But one thing it's not doing is decreasing. Yeah. Now, so we could go the other way. Let's look at the other way. We can say, well, what about this one? Here we have this one's going down and then it stays the same, maybe goes down some more. This right here, this is monotonic. Okay, this is monotonic. But this is non-decreasing. I mean non-increasing. Because notice that every term is bigger, well, it's less than or equal to the previous term. This is monotonic non-increasing. Okay. So we've got this terminology when we talk about monotonic. Okay, we have non-increasing monotonic and non-decreasing monotonic. Now, added on to that is we've got bounded sequences. So let's look at this. Okay, now I'm going to put a little line right here, and let's suppose that this sequence never gets bigger than that line. There's no term of the sequence that's ever going to be bigger than M. Okay? We say that's bounded above. Okay, that's bounded above. Now, that particular sequence there is monotonic and bounded. Now let's look at a sequence that's bounded but not monotonic, or bounded above but not monotonic. Okay, let's just look at this one here. Now that that is bounded above, but it's not monotonic. Okay, so we have a sequence here that's not monotonic, but it's bounded above. It's never going to get any bigger than this little dotted dashed red line up there. So we have a situation where you have bounded above. Now you also have bounded below, and you can probably, you know, you know what that's going to look like. Okay? So maybe we'll have something that looks like this. Bounded below. Monotonic and bounded below. It's not going to get any smaller than this. No term is going to get any smaller than N. Now, what if it's bounded above and below? So you can have a situation where you have bounded above and below. So let's look at that. Whoops, not that one. Let's do this one. Okay, here's bounded above and below. See, something like that. If we see a situation like that, where it's got a bounded above and below, we just say it's bounded. It's bounded above and it's bounded below. So we just say bounded. Now, here's the thing. If you have a monotonic sequence that's bounded, then that sequence converges. Okay? So if let's suppose we've got this sequence, and let's suppose it's monotonic and bounded, then it converges. Yeah, then it converges. Okay. Now, let's look at some examples here. Let's suppose that we've got this sequence here. Let's suppose we've got a sub n and it equals, oh, let's say 1 over n. Now, this sequence is definitely monotonic. Every value of n, as you put in larger and larger values for n, this sequence here, each term is getting smaller and smaller. So you put in a 1, you get a 1. You put in a 2, you get a 1/2, 1/3, 1/4. Okay. Now this sequence is monotonic, and it is bounded. This sequence can never get bigger than 1, and it's never going to get smaller than 0. So we say, okay, that sequence there converges. Now, let's suppose we've got another sequence. Let's suppose we've got, um, let's say, n squared over 1 plus n, that one. Now, that one is monotonic. However, it's not bounded. Now, it's bounded below, but it's not bounded. So this one, we can't say this one converges. This one is just getting larger and larger and larger. So that's an example of a divergent sequence. So the first one converges, the second one diverges. Now, let's look at one that's bounded above and below, but does not converge. So this one. This one is bounded above by 1 and is bounded below by -1. It's going to oscillate between, you know, it's not going to get any bigger than 1. It's not going to get any less than -1. So this one is bounded. However, it's not monotonic. So this is another example of a sequence that diverges.